All right. So I've been trying different things in my videos. I was doing a little programming for a bit. Um, I was getting a bit stuck on making good progress with the programming stuff. So I got a recommendation that maybe I should get some math stuff. Ooh. And all right, I had to sort out a little bug there. Not really a bug. Good Notes has like a presentation, has options for presentation mode. And if it's in something besides entire screen, then the way it plays with Reflector, which is the app that I'm using to mirror my screen to my iMac, is kind of weird. Where it like will reset the location of like the iPad display on my iMac, and like whenever I change back to the app from another app. Whereas if I have it on entire screen, then it's fine. So, so anyway, um, so I'm looking at this math book. It's a book I've looked at before, a PDF of it. The Art of Problem Solving, and it's Prealgebra, so it's like the first book in the Art of Problem Solving series. And where's the there we go. Table of contents. You get some some sense of like the subject matter. I looked at this a few years ago. I worked through the whole book. Um, and so they start with arithmetic, they do exponents, uh, multiples, prime factorization, fractions, uh, equations, decimals, ratios and conversions, percents, square roots, getting into some like basic geometry stuff with angles, perimeter area. Um, they have some basic data and counting stuff, but the focus, is sort of on the rudiments of math knowledge and skill. Um, they do they don't start from like a total blank slate. Like they're not like gonna teach you really how to add two and two per se. Um, but what they focus on is like having a conceptual understanding of why these things, like addition, multiplication, all that, like how they operate, why they work. Um, so it's not really a good book if you're trying to teach like a 4-year-old math or something. I mean, like probably like there might be like there's 4-year-olds that I think have done like advanced calculus. So like it depends on the 4-year-old. But if basically you had you know the sort of some exposure to mathematical concepts that a lot of people get in school, um, like the basic stuff, adding, subtracting, times tables, that sort of thing, and you want to have more of an understanding of like why it works as opposed to just just it being like you put numbers into an algorithm and you get the right answer, then this could be a good book. Um, I've looked at other math books before, and this is difficult, like especially if you try and do all the problems, because some of the problems are pretty hard. But it's good. So I thought I would just look at this again, since I haven't looked at it in a few years, based on the file modification dates in Mac OS that I saw. And since I've already looked at it and just see how much I can explain and how much I like remember, in order to try and figure out like what my actual baseline math level knowledge is. I got a suggestion because I was struggling with some of the programming stuff that maybe I should try and look at some basic math stuff. And maybe that would be easier. So I figured, well, I mean, hard to get much easier than stuff I've like already looked at and worked through and, you know, wrote a bunch of some notes in the margin on. So you see, they say, what's the best way to? All right, so I just highlighted this bit, and they say if you only understand how techniques work, but not why they work, you'll have a lot more difficulty modifying those techniques to solve more complicated problems. So that gives you a sense of like their very general pedagogical approach. So now I was looking at this, that, and I was like, okay, how much of this do I actually remember? Well, now we're in GoodNotes, and I just pasted like a cropped image from the book in GoodNotes, which is how I did this last time. Now, of course, I know that -5 and -7, if you multiply them, you get a positive number. I'm trying to, like, can I actually explain that though? I know that there is a good explanation that I knew at one time. It's not coming to me right now. So I'm just going to skip that one and see if it comes to me. And if not, I'll just read and find out again and see if it's in the nature of, I instantly recognize and can add a bunch of details, and so it was really inside me the whole time, or I'm like, oh, that's new information. So the rest of these though, I think are pretty straightforward. So the second one here, and now, of course, one way, like, a lot of people could figure this out taking a long time, including me. Where you just like multiply, like, where you have the numbers on top of each other, and you're like, okay, control my iPad here, right? And you just have it that for a while, and then you do the other one, and then you subtract them. But you'll note that what they say is, and be able to compute this in your head. Now, if you can do that, if you can do the like long form, multiplication stuff with 4-digit numbers in your head. I mean, I don't think it's like impossible, but that's more pro skills than I have. So the way to think about this is the following. We have a couple of big numbers, and these big numbers both have as one of their factors the number 1990, right? So, and I'm sort of Like, I think I know this, but I'm sort of trying to explain to make sure I know it and to check my own like understanding. So, so imagine you've got like, say you've got something like this. My handwriting is terrible. 5 times 4 minus 5 times 2. Okay. Now, that's easy enough that like most people can just bam do it in their head and figure it out really fast, or even just like see it, just like they know the answer. It's like before I'm done writing it out, right? Um, but let's just do it a different way, just to illustrate the principle, and then we can double back and apply it to the problem with the much bigger numbers. So, what is multiplication? It's repeated addition, right? So when we say 5 times 4, we basically mean that we're doing 5 plus 5 plus 5 plus 5, or it looks like S plus S, or whatever, minus, I'm going to try to do the 5s a little better, 5 plus 5, right? Now, all right, so if you think about it, like really, where's my lasso? There it is. Okay. This is like the simplest. Well, I mean, you could do simpler even, I guess, if you just had a bunch of ones. But so this first step here is like the right. So the first level here is the simplest. We're just doing addition. Maybe like the simplest or most basic way to represent that, and then the multiplication is just a more shorthand way. There's another way we could represent things, though, which is we could say something like, well, I think of this as sort of an intermediate stage. Um, where we have 5 and then another, or actually let's make it even clearer. Well, yeah, I think the meaning of the parens is pretty clear. And then likewise, okay. So 5 times 1 plus 1 plus 1 plus 1, and then subtracting from that 5 times 1 plus 1, right? Now you might think, well, having that many ones is a little silly. So why don't we just do, when we add them up, and then we'd say 5 times 4, and then minus 5 times 2, right? Oops. Let me keep the parens in there for now. And then we see that the last step is just a rewriting of um, the previous. So, these all of these mean the same thing, right? The reason I'm belaboring this is because I think it's helpful to have a few different ways of representing this pretty basic, mathematical expression for when we wind up doing something like this, so you know what is happening. So if I recall, what I just did might be described as like factoring a 5 out of an expression. Like, they might have called it that in school or whatever. And you might know, like, algorithmically, that's what you're allowed to do, but the issue is why. And so one way to think about it is this. So we have some 5s, and we have some 5s, and then we're subtracting some 5s. And the 5s, all we have are 5s, in a way. Like we're not, we don't have 5 and then we're subtracting a 3. We just have different groups of 5s. The 5s don't change. It's the number or instances or copies of 5 that are different. Whereas, on the left side, we have 4 5s, and on the right side we have 2 5s. So because both sides of this expression, like the left and the right side, just consist of 5s, that's something that they have in common. So when we factor something out, we're saying, okay, the 5s are in common. Both sides of this expression are just like a different number of instances of some 5s. So, and it's that number of instances that's different. So let's put the 5 thing to one side and just consider the difference. And then we can bring the 5 back in at the end after we figured out the difference. And so that's what we do. Another way to think about it, and it's pretty similar, but like a slightly different way of describing it, is, we have 2 numbers, and, this, the number on the left side, 5 times 4, and the number on the right side, 5 times 2. And that number, those numbers, whatever they are, they both are made up of 5. So, and again, it's a bit repetitious, but like, since they're both made up out of 5s, and use that fact and, again, put the 5 to sort of one side, figure out the difference in the numbers of 5s, and then bring the 5 back into it at the end. So, and you see some gain from doing this approach, I think, even with a simple example where, instead of, although it's not nearly as obvious the benefit as with the more complicated example, because, instead of having to figure out 20 minus 10, which is what we would have to do, we just, we figure out 4 minus 2, and then, that becomes 2, and then we multiply 2 and 5, so it keeps the numbers a bit smaller. So that's the basic idea. Now, how do I want to do this? Maybe I'll... Okay, I'll shove that there. Okay, so... We'll box around. Okay. So now with this more complicated example, I think it's kind of the same idea. So we've got 1990 times 1991 minus, and I'm just going to rewrite the 1990 first because I just want the 1990 on the left side on both. Times 1989. And so, again, one way to think of it is, well, we have some number on the left, some number on the right. Both numbers have 1990, they're made up of some number of 1990s. So we can put that to one side and say, okay, well, let's just figure out the difference in the number of 1990s they're made up out of. So 1990, 1991 minus 1989, and that's 2. So we have 1990 times 2, and then that is 3980 is the answer. So with the next one, with the dividing by a fraction, the best way to understand this is in terms of like a pie. Like if you're dividing by a fraction, you want to figure out like, okay, if I took, let's assume it's a whole number, like in this case. But let's just take 1. So, oops. So let's say we have 1. I want to divide it by, we'll use the same fraction, 1/7. Actually, before we do that, let's even consider maybe a slightly simpler case. So we'll just put that off to one side for a second. So suppose you had, make it really easy, 6 divided by 2. Okay. Now most people would be able to figure out that that's 3, right? Now what about 6 times 1/2? Well, it's the same result. These are basically like equivalent expressions. If you do 6 times 1, you get, 6, and then you have the 2. And then so this is, these are just different ways of saying the same thing. And 2 goes into 6 3 times. There's a higher level way of understanding or thinking about this than I'm gonna be able to go into right now, because I don't know how to explain it super great. But basically, dividing by something or multiplying by the reciprocal of that something is like the same operation. So going back to this example, we'll just tuck that in a corner. Yeah. Oh. Okay. So, one way of thinking about dividing wholes as well, we've got 1/7. That could be, slice of pie, say. So we want to know if we're dividing a whole into sevenths, how many how many slices do we get? And people, would intuitively just say 7, right? Like that wouldn't be too hard. But probably mathematically, it's like what you do in the algorithm is you say, okay, well, we have 1, and then we multiply by the reciprocal, right? Which is what I was talking about just a second ago with the 6 and 2 example. So then we get 7. To make intuitive sense that you have to multiply if you're slicing something up, because you're taking a whole and breaking it into parts, so you're going to need a bigger number. So you can't, if you're dividing something into, dividing a whole into parts and then you're generating a smaller number than what you started with, then something has gone wrong. I feel like I had something to say about the third example, but not as much as the second. So first example, Couldn't really explain well. Second example, I had a lot to say. Third example, And then let's do the fourth example. Okay. They didn't used to have this little imagey thing in where you could just in GoodNotes where you could just drop things. That's a new thing that they added. That makes it way easier than the method that I used to have to use. I haven't used this app or done this sort of workflow in a while. So, okay. 4 times 10 times 49. And then, so when you're divided by something, you can represent it in this way as well. 2 times 5 times 7. So since you can see it in the first representation here, I just sort of skipped to doing a different representation. So this problem comes down to like thinking about factors. So these numbers are both being multiplied. So we've got like one big number over here and another number. And we want to break it down, simplify it, and calculate. And they give us the answer, but we want to be able to do that in our head. So, looking at this, I'm gonna write things out because I want to be explicit, but like basically, we have a number at the top here that has a bunch of factors that can be more broken down. So rewriting the top number. So 4 could be 2 and 2, and 10 could be 2 and 5, and 49 could be 7 and 7. I don't like that 7. There we go. And then the bottom is the same. But then you can do canceling where you say, okay, so we'll cancel some of the 2's, cancel out the 5's, cancel out a 7. And we have 2 times 2 times 7, which is 28. And, mentally, you could just do it, well, you could do it something like, well, the bottom 2, we can divide that top 4 by 2's, and then we have 2. And then we could divide the 10 by the 5 on the bottom, so then that's another 2. And then so then right now we've got 4. And then we can divide the 49 by the 7, and we get 7, so that's 4 times 7, which is 28. It's just another way of doing it. So that one I think I'm pretty solid on. So let's go back to the, no, we don't want to go there. Hang on. All right, so back to the text. Let me adjust my microphone here. Got a bit of a weird setup here with my iPad and my microphone. So I'm talking about the number line some. I guess here they're talking about some terminological issues, and they say that their terminology is going to be positive integers for 1, 2, 3, non-negative integers for 0, 1, 2. So they're trying to be extra clear, which is good. Addition. So, oops. I think it hadn't like downloaded uh, iAnnotate hadn't downloaded the file locally because I hadn't explicitly told it to. So it was like loading each page from Dropbox at a time, and that's why it was like blurry. But I was like, no, I got plenty of room on this iPad for local storage, so I want those right away. By the way, when I first worked through this book a few years ago, um, iPads were worse enough that I had to I made like an optimized version of this PDF that was smaller, so that I could actually use it I could view it on an iPad. Um, but now, I mean, my iPad isn't even like the newest one, but it's plenty powerful to handle like the full size original scan or whatever. So it's just computing technology is great. So problem 1.1 is very straightforward. If you say, here's 2 apples and then here's 3 apples, uh, it doesn't, it's no different in terms of the result than if you say, hey, here's 3 apples and then 2 apples. I should have said, how many apples are there? Like it doesn't, if you have like, the same size groups that you're adding up, it doesn't matter the order. So 1.1 is very straightforward. 1.2, using the 2 pictures below, explain why 2 plus 3 plus 4 equals 2 plus 3 plus 4. Right. Same principle, I think. Um, like the particular ordering of the grouping not mattering for addition applies regardless of how many groups you're adding up and, whether you do. Indices are just a way of saying, like, add this group of things first, but the order of addition does not matter. So it doesn't matter whether you're adding 3 things with one group of parentheses or 10 things with 7 groups of parentheses. It doesn't matter. It only applies when we're just, or I should say, only speaking in the addition context right now. Like they have an example here where order does matter. Order of operations does matter. They say 3 plus 4 times 5 equals 7 times 5, which is 35, whereas 3 plus 4 times 5 equals 3 plus 20, which is 23. But the difference here is that they introduce multiplication. So, using the properties from problems 1.1 and 1.2, explain why 4.72, or sorry, 4.72, 472 plus 219 plus 28. Right. So it's the same idea. You've got, A, B, and C, and you're just adding them. It literally doesn't matter whether for the result. It matters for like the intermediate computations that you're performing, but it doesn't matter for the result whether you add B and C first and then add that to A, or whether you add A and B first and you add that to C. It just doesn't matter. Compute the sum. Okay. 472 plus 28 is 500 plus 219 is 719. Compute, right. So what they're doing here, I'll like do this. Do I haven't used iAnnotate in so long. Let's use blue maybe. Okay. How's that? Oh, that's way too thick. Okay. There we go. Yeah. So they've you've basically got sort of paired off numbers here. 2 and 8 are paired. That's a 10. I'm just gonna write it down here. 10. 12 and 18 are paired. I'm saying paired because it's like you add them up and they come out to a nice neat number. That's 30. 22 and 28 are paired. That's 50. And I'm guessing the next one's 70. Yep. It is 120, 150, 160. So I could have done that in my head, but I just wanted to show the like the matching. Find the sum. Oh, one of these. All the positive integers from 1 to 20. So the way to do this is not to do 1, 2, 3, in my opinion. There's a reason they just showed us like that problem where the numbers were part of, because you have like 1 pairs off with 19, that's a 20. 2 pairs off with 18, that's a 20. 3 pairs off with 17. Oh, I should. 4 pairs off with 16, and so on. And it continues like through. I'm just gonna dot this. The 9, because 9 and 11 pair off, and that's also a 20. So we've got 1 through. So basically, the numbers 1 through 9 pair off with another number under 20, add up to 20. So that's 9 sets of 20. But then there's this sort of the bookend cases. So we've got 9 sets of 20, but then we get to 10 and 20, the actual 20. When you add those up, that adds up to 30. So then 9 times 20 is 180 plus 30 is 210. And the book actually has like a more efficient way of doing it, but I forget the details of that right now. So this is one way, which I think is pretty clear, and you could pretty much do in your head. So all right, so back to the problem 1.6. Right, if you add nothing to a number, you don't change it. Right, so now they're going to talk about the answers. First row has 2 squares. Second row has 3 squares, so there are 2 plus 3. Now let's look at the picture on the right. The first row has 3 squares, the second row has 2 squares. In total, there are 3 plus 2 squares. The picture on the right, however, is just an upside down version of the picture on the left. Flipping the picture upside down doesn't change the number of squares. So we conclude that 2 plus 3 equals 3 plus 2. Pretty straightforward. Whenever we add 2 numbers, the order of the numbers does not matter. For example, 5 plus 17 equals 17 plus 5, and yada yada. There are an infinite number of such examples. And then can't write down an infinite number. Instead, we write the equation first number plus second number equals second number plus first number. This is a long equation to write. We can shorten it by letting A represent the first number and B represent the second number. See, I like this. Sometimes in a math text, they'll just be like, here's a formula thing. And like literally just slammed in there with maybe some like technical, like mathematician level definition of it and kind of no context. Whereas this is like slowly working its way up to the abstract generic representation. So I like that a lot. Here A and B stand for any numbers, possibly the same number. For instance, if we let A equals 2 and B equals 3, then we have our original example, and then they give a different example. Okay. The rule that A plus B equals C for all numbers A and B is called the commutative property of addition. In problem 1.1, we explained why A plus B equals B plus A is true for one particular example. One example doesn't prove it. We don't have the tools to explain why this must hold for any two numbers. Right? They're just trying to give us an intuition. What if we had three numbers? Right, so they call this the associative. I never could remember these. I mean, like the principle is the same. So giving, I mean, there might be some reason for it, but giving each name like a special. And I realize there's like grouping involved in the associative thing, which is why it's like they're associated, haha. But it still seems weird to me. In the commutative property, the numbers are moved around, commuted on the two sides of the equation. In the associative property, the numbers stay in the same place, but are grouped differently. Together, the commutative and associative properties are sneakily powerful as they let us add a list of numbers in any order. The thing that bothers me about the breaking it up into things, because I see the principle as like for simple addition, like ordering, grouping, none of it really matters. But I think maybe because people do math proofs and stuff, and so having stuff as like broken out into like a logical proposition that you can reference, like according to the associative property, that could be valuable. So, okay. So using the properties from 1.1 and 1.2 explain yada yada. And doing a sort of logical proof is basically, I mean, it's not really a logical proof, but like they do it very step by step. You see here where they have the initial expression, and then they take the expression on the left side, and they say they use the commutative property to oops, no, that's not what I wanted. Ah, wrong thing. Oh, that's fine. It's because they're close together. I'll just do this then. So they use the commutative property to flip the numbers around within the parentheses, and then they use the associative property to group the parentheses differently, and then they've proven they have the exact same expression in terms of result on the left as on the right. Right, and then they did the actual math the same way I did, where they added 472 and 28 first, which is the best way to do it. Point of problem 1.3 is that we can arrange the numbers in our addition to make the addition easier to compute. It's easier to first compute 472, then compute 500. Yeah, okay. Oh yeah, they did. They did 1.4 in a better way than I did. Because they saw. Yeah, fair. They saw that you could pair things off into 40s. So then each pairing is a 40, which is better. Like the more regular you can make stuff, the less you're less likely to make an error with like 40 plus 40 plus 40 plus 40 than you are with like, 10 plus 30 plus 50 plus 70, I think. So that's cool. Yeah, and they also did this one a little differently, I see. Right, so yeah, I think this way they did it is also better. Than what I did for problem 1.5. Because you actually just you get 10 identical pairs. So that's the principle of like 1.4 and 1.5. If you can get the same, if you can pair things off into the same unit, that's better. 40 or 21 or whatever it is, as opposed to, having different sized pairings that result in different sizes. Like I'd paired most of problem 1.5 off into the same thing, but then I had like the special cases at the end, but that was unnecessary. Right. And then I has 0, a plus 0 equals a. That's an easy one to remember. Right. Exercises. I've got the solutions manual too, but I don't think we'll need it for these. So this first one is easy because we've got 99 and 101. That's 200, and we've got 3 of those, so that's 600. So that's straightforward. This next one looks similar. There's like the numbers are bigger, but the principle is the same. So we've got 1999 and 2001, which is 4,000. And we've got 4 of those. So that's 16,000. Let's see. Right. Right, so with the improved focus on pairing off things into identical pairs if possible. So 3 and 47 are 50. And so we're 13 and 37. It looks like we've got basically 5 pairs of 50, which is 250. And this one is pretty fun. So we basically got 1 and 99. That's 100. 2 and 98. That's 100, and so on. And likewise on the other end, 49 and 51 is 100. 50 and 50 is 100. And so we've got 50 pairs of 100, which is 5,000. And I've checked, and all those answers are correct. So I've got the solutions manual open. Okay. I'll call that a video here, and might continue to the next section next time.